All right, let's get started. Well, good morning, everybody. This is Arun Thiraviam, and I am a simulation product specialist here with GoEngineer. Thank you for joining us today for our simulation product webinar series. Today, we're going to spend some time talking about SolidWorks Plastics, the injection molding simulation tool that's built into SolidWorks CAD, uh, and how this tool would assist you, giving you valuable manufacturing insights while developing plastic products. Well, you've been muted for the duration of this webinar, but as soon as at the end of the webinar, we'll have a short Q&A session on SolidWorks Plastics. All right, let's get started. Now you see these four products on the screen. Now, what do these four products have in common? Well, besides the degree of sophistication and the amount of technology that went into designing these products, now you will all agree that each of these products have a plastic component in them. And what's so special about plastic component is the amount of sophistication required in order to actually manufacture the component. So typically 90% of the plastic components are manufactured through the injection molding process. So who are the typical stakeholders in this injection molding process? Well, there are two essentially: the guys who design the products and the guys who manufacture the products. As far as the designers go, they have very straightforward targets as far as their performance for the plastics products. But what about why would they need to worry about manufacturability? Because all the crazy, features and the crazy design geometries that they propose for the functionality of their product needs to be manufacturable. And at the end of the manufacturing process, we need to make sure that the plastics maintain the structural and aesthetic quality they are intended to be designed for. And finally, if the designers would like to try something new, they'll need a tool by which they can simultaneously validate the manufacturability of the plastic product while without compromising any of the structural or aesthetic aspects. Now let's look at what the manufacturers think about as soon as they get the product. Now, what do the machine cycle settings have to be? Where should the gate locations be? And finally, how many mold revisions could they avoid by actually getting valuable insights on the injection molding process prior to actually manufacturing the product with an injection molding machine? Now, what we are proposing with SolidWorks Plastics is essentially a virtual injection molding machine tool by which you can plug in all these parameters such as the cycle settings, the gate locations, the type of plastic that you'd like to apply to your product, and validate its manufacturability while justifying its structural and aesthetic qualities. So in order to justify that, here's a little example that I've set up. So I've essentially taken a drone and I've pulled out a component from the drone, and then I've essentially went through different phases on changing the existing design and optimizing the design. Now, so here's my general roadmap for the process. So I started out with an initial design, I tested it, I changed the design, tested it again, and I finally set this through a design optimization path and tested the optimized design as well. So you'd notice you see a little pattern in this entire product development process. The pattern being at every stage of a design change, I not only test the design for strength, but I'm able to test the design for manufacturability thanks to the concurrent product development tools that's just built inside SolidWorks. Now, as far as the case study goes, I mentioned I'm going to use a quadcopter, and this is what the quadcopter looks like. It essentially has 4 arms and a frame. What I'm going to essentially do is try and justify the injection molding of this arm using, say, a plastic like ABS, and study the various structural qualities and the manufacturing defects I can expect by virtue of the injection molding process. All right, let's get into the software. Now, with this pseudo-optimized design inside SolidWorks, now how do we essentially validate the manufacturability? Now, SolidWorks, as its philosophy, is moving away from just being a CAD tool to a complete solutions product. So you have these different tools that are built in that enable you to test, design, test, and validate your products for manufacturability. Now, all those tools are available under the add-ins tab. So if you move into the add-ins tab and check the SolidWorks Plastics button, a couple of things happens. Now, uh, the command manager ribbon essentially updates to have the SolidWorks Plastics Manager, and the feature manager tree also updates to have the little SolidWorks Plastic Manager. Now, this way you're able to set up uh, your injection molding simulations within just the CAD interface. Now let's take a look at how we set up a typical plastics analysis. So you can see as soon as I check the little plastics button, I have a plastics manager tree that has a couple of items. Of course, for any finite element any software driven by finite element analysis, meshing becomes a necessary evil. As far as SolidWorks Plastics go, there are two kinds of meshing algorithms that are available. One being the solid mesher, the next being the shell mesher. Well, the shell mesher is good for uniform wall thicknesses, which is the first cardinal rule of plastics product design. But anytime you have crazy shapes such as these that have uh, varying cross sections and multiple features, it's recommended to use just a solid mesh, so you're able to study the non-linearity of the plastics flow within your product. Okay, now how does this meshing process work? Now if you right click solid, there are two ways by which you can mesh this model. You can either use the automated measure feature that's built in, which is quite robust, or you can go into the manual measure and control how many little elements this little geometry can be broken down into. Now going into the solid measure, by right clicking it and hitting the manual, brings up a little meshing wizard tool. All I need to do is go through each of these items in the wizard tool and make sure that I'm able to mesh the model and validate the quality of the mesh. So starting off in step one, I get to pick what kind of mesh I'm applying to the model, and if I'm going to mesh both the runner and the cooling channels, and if I'm going to include a virtual mold. For this analysis, I'm only going to mesh the arm. I'm not going to include any runner system or cooling systems. Now as soon as I hit the next button, now the SolidWorks has the plastics has the ability to mesh multiple components or injection mold multiple components. So it tells me how many cavities and how many runner systems and how many cooling lines I have in this set domain type. Now, since I have just one component, I have just one cavity. Now, as soon as I hit next, here's where I'm able to decide what triangle size I can apply to the model in order to justify the accuracy of the calculation. So this is essentially where you'd run the analysis with the specific triangle size, reduce the triangle size, rerun the analysis to see if your results change. Now, if I use the default triangle size and I hit the mesh button, you can see that the mesh is quite coarse and it may not be really, it may not offer the flow paths represented by the actual geometry in order to justify manufacturability. So I'm going to try and reduce the triangle size by a little bit. So initially it was about 9 millimeters. Now I'm going to reduce it to about 4. Well, this doesn't seem fine enough, and since this does not constitute a whole number of elements, I can be a little adventurous and set it to a really small number. Now 6,000 elements is a good or 6,000 triangles is a good place to be as far as meshing such a small model goes. So I'm going to accept the new triangle size, and you can see that you have sufficient refinement with the current triangle size across the thickness and across these different ribs in your geometry. Now once I've set the triangle size and I've meshed the model and I hit the next button, I get a quick snapshot on the quality of the mesh. So I need to make sure that this mesh is waterproof, that there aren't any holes or gaps in the mesh model. And finally, what the aspect ratio of my elements are. I wouldn't want too high aspect ratios in my elements that might compromise the accuracy of my results. Now, based on this little snapshot, I'm able to use small tools within SolidWorks Plastics in order to manipulate the mesh and improve the quality of the triangles. Now, that is a discussion we'll save for later, but since from the snapshot we can justify that the mesh is fine enough and there aren't any there aren't any errors or any erroneous triangles, let's just move on. Now, the first 4 stages essentially captured only the surface of the geometry. So how SolidWorks solid meshing works is you initially capture the surface of the model by justifying the accuracy of by justifying the quality of the triangles on the surface, and finally use the surface triangles to generate the internal triangles to ultimately create a solid mesh. So as far as the solid mesh type go, there are two types of meshes. There's tetrahedral and hexahedral. Now, without going into too much detail, now the tetrahedral works for a majority of models with complex curvatures. So let's just stick to that. Now once inside the tetrahedral type, there are sub options. Now I can use either pure tetrahedrons to capture the internal geometry, or I can use a combination of prisms, uh, you know, uh, prisms, pyramids, and tetrahedrals in order to capture the internal geometry. Now, just to give you an idea what the hybrid mesher looks like, I'm going to choose the hybrid and I'm going to hit create mesh. Now what that does, like I said, is it meshes the internal geometry. Now using the hybrid mesh ensures that the elements that are closer to the surface are as flat as possible to capture the boundary layer, while the elements on the inside are still left at triangles to save on computation time. Great. Now that we have an idea, now that we meshed the model and have an idea of its quality, let's accept the rest of the menus in the wizard tool and finally solid mesh the model. Now once the model has been solid meshed, you can review the mesh by hitting this little mesh model button on the command manager in your plastics manager. Okay, great. Now you'll notice a couple of things has happened by virtue of the meshing. Now this has opened up the entire input tree in order for you to set up the analysis. So after you set up the mesh, the first thing you do is get in and apply the material properties. Now as far as material properties go, SOLIDWORKS Plastics has a material database of over 4,000 materials. Uh, and each of these materials are sorted either by the family of polymers they belong to or by company. You also have a little search tool that enables you to search for the material that you'd like to apply to your plastic. And you're also able to customize these materials based on, um, you know, custom plastics that you might be concocting in your respective R&Ds. Now, just in the default database, I'm going to use a standard ABS. I've heading into sort by family, I'm going to use a generic ABS material in order to injection mold this plastic. Now once I've selected the material I want to use, I hit OK, and I see the little green check mark indicating that my polymer has been assigned. Now once this is done, I head into the process parameters and I set up the various injection molding parameters that I'd like to study the product for. So essentially injection molding, according to SOLIDWORKS Plastics, occurs in three stages. There's the fill stage that does that that fills the cavity of the plastic. There's the pack stage that then packs the cavity and enables for the plastic to cool down. And finally, there's the warp stage that controls or that gives you results into what the plastic product looks like as soon as it is ejected from the mold. Now, right now, since we are only trying to gain initial insights into the manufacturability of the product, let's only assign the fill settings. Now, once I head into the fill settings, a couple of things uh, you'll notice is that there are default parameters that are assigned. So based on the size of the model and based on the type of plastic you use, the mold temperatures, the melt temperatures, and the injection pressure limits are automatically dialed in, and the fill time is automatically calculated. Now you can override any of these properties, but like I said, while we're at at this initial initial design stage, it's best to leave these at just defaults to have an idea of how the manufacturing defects play out and if these default process parameters essentially work for the product. If they work, you can keep them, or you can change them based on the injection molding machine that you have in-house. Great. Now once I've set up the fill setting, now the only thing that's left to do is set up the gate location. So moving down the tree, uh, below the material and process parameters under the boundary conditions, I can set up the gate location through this little injection location menu. Now if I right click injection locations and I open settings, now I'm able to uh, select the injection point on the different parts on different areas of my model. Now if you're not really aware of where an ideal injection point should be, if you do not have the experience, if you too much experience with injection molding, you can actually set the pointer diameter and get SolidWorks to predict where the injection point could be as far as based on the geometry of your model and the volume of the plastic that you're about to fill. So since this is center, the injection location, uh, by virtue of automatically adding the injection location, I'm going to keep this setting. I can also predict the flow pattern based on setting specific injection points, indicating that these areas are going to be the last to fill and probably the most difficult. Great. Now, now that I've set up the injection location, I'm going to accept this little location. And after this, all I need to do is run the analysis. So based on the process parameters I've set up, I can either run just the flow or the fill analysis, the flow in the pack, or the flow in the pack and the warp. Now I'm just going to switch to an analysis that I've already set up, and I'm going to activate the access the flow results. So as soon as I've run the flow analysis, you'll notice under the results tab, there's a little flow results item that shows up. In order to access the result, I double click on the flow results item. Now the first thing I'd like to see is, hey, what's the fill time? So this took about 1.13 seconds to fill. Now I can get results such I can even animate the fill in order to see where my potential well lines could occur, or where my potential air traps could occur, or I can actually select the appropriate manufacturing defect items off of the flow results tree in order to in order to inspect both of those things. Now, besides getting a fill animation of the cavity, I also have a little results advisor tool that gives me information about the quality of the manufacturing, in the sense that, hey, what was the injection pressure limit reached in order to manufacture this product, and how can I essentially improve or reduce this injection pressure limit to ensure that my product is manufactured at the given time, but with a much smaller injection pressure. Now, besides that, what I'm worried about specifically with this product are two things. Now, this constitutes a big piece of plastic that this is about to fill, so I essentially want to see how long this takes to cool. Now, if I hit the cooling time results, I can see that this takes about 21 seconds to cool. Now, I can access the clipping plate mode to essentially see where this 21 second resides. Of course, the surface of the plastic is the fastest to cool, and all of these little bosses take the most amount of time to cool. So with solver plastics, I'm able to see not only the results on the surface of the model, but I'm also able to draw these little cross sections and integrate the model for you know uh, where for what could be the likely cause of a lot of defects. Now this boss not only increases the cooling time of the model, but if I switch to the sink marks, I can see that I have a sink mark of about 0.09 millimeters right on the top surface. Okay, great. Now that I have insights into the quality of the plastic during the manufacturing, now what can I change in order to improve this you know design? So what I've done is I've added a uh, little cut right on the surface. Now the purpose of that cut is twofold. A, I'm able to mount the rotor within these cuts, and B, I'm able to reduce the area cross section, or rather the thickness in the area of this cut, in order to hopefully reduce the cooling time and also reduce the sink mark. Now going back to the project I've already set up and accessing the flow results. Now I can integrate almost the same thing. So as far as the fill time goes, now it took a shorter amount of time to fill by virtue of the change. Now as far as the fill pressure goes, the previous fill pressure was around 60 megapascals. Right now this is about 64. The slight increase in the fill pressure, the fill pressure there. And finally, the cooling time. You can see there's a drastic reduction in cooling time by just making such a simple geometric modification. Now accessing the clipping plane mode indicates to me that the area that previously took the longest to cool has now significantly reduced cooling time. Now how did this affect the sink marks? Again, you can see the sink marks in this area has significantly reduced by virtue of reducing the size of the bars. Finally, I'm able to see information such as the well lines and the air traps on the different areas of the model. Okay, great. Now that I've varied the geometric property, now what have I essentially compromised here? Now that I varied the geometry of the model to improve the manufacturability, I should be able to test the product for strength. because I've removed material. Now I'm able to do this just within SolidWorks by removing the plastics add-in and by adding the SolidWorks simulation tool. Now again, SolidWorks simulation is a structural validation tool just built into SolidWorks that enables me to validate the structural strength of the components by making these small design changes. So with my initial design, I've set up a really simple analysis. I've assigned the ABS material, I've assigned a fixture at the base, indicating how this component is fixed at the frame. I've applied boundary conditions indicating the direction of gravity and the lateral force that um, this little arm experiences during flight. Now with all of these conditions, I'm able to see the stress distribution. Now this number needs to be below 30 for ABS, so we have a sufficiently large factor of safety. And finally, the displacement. Now if I'd like to run a comparison between this and the modified design, I've already set up an analysis for the modified design. I can hit the little compare results tool. To have a side-by-side comparison between my initial design and the final design. So you can see by virtue of the stress distribution that there's not too much of a change between the two components as far as stresses go and as far as the displacement of the end goes. So let's quickly summarize this exercise. By comparing the results between the initial configuration and the modified configuration, I can see that I've reduced the fill time with a slight increase in the maximum injection pressure. Now, as far as sink marks go, I've managed to displace the sink marks from the center to uh, out of the critical area where I'm going to be mounting the rotors. So you can see that there was a 10-second reduction in cooling time by virtue of that little design change. And finally, we were able to use SolidWorks simulation to validate the structural performance of the component by virtue of this change in order to have a product that's been tested for manufacturability and structural strength. So the summary of that little process was, hey, I used 3 design criteria to justify design change. Now, how am I going to use these 3 criteria in order to optimize the product? Now with SolidWorks simulation, I have a structural design optimization tool that lets me control different geometric parameters. Now I need to give this little structural optimization tool 3 inputs. The variables, here the variable was the depth of the cut as indicated in this little screenshot. Now I vary the depth of the cut from an initial value of 1.5 to a final value of 2.5. Now, as far as the constraints go, that's the second piece of information I need to translate to the software. Now, the constraint essentially monitors how the displacements, the factor of safety, and the stress distribution on the component changes by virtue of these design change. Now, finally, with the optimization tool, I'm able to specify to the software what I'm running this analysis for, which is essentially to minimize the mass of the product. Now, what the optimization tool does is it sets up a set of standard iterations. Now here it set up 3 iterations ranging from 1.5 to 2.5 millimeters. Now based on these 3 iterations and the results from the iterations, it essentially proposes an optimal design. Now you notice that we started out with about 20 grams for the initial design. Now using the optimization tool, we got down to about 18. Now let's take a look at how this essentially affected the manufacturability of the product. Well, the optimization tool is called the design study tool. This is just to show you what this looks like inside the software. Now this is the structural analysis test that was essentially run, that the optimization tool reruns for different configurations. And I'm able to toggle between each of these configurations and view the results for each one of these configurations just within the optimization tool. Now that I've managed to reduce a couple of grams off of the project, now I'm going to try and validate the manufacturability of the product using SolidWorks Plastics. Again, removing the sim add-in. and turning on the plastics add-in. Updates a little command manager to have the plastics options and the feature manager to have the plastic study. Now, again, I've set up this analysis already prior to the little webinar. Now, I went through this essentially the same solid meshing procedure, applied an ABS material for the plastic, but this time I decided to run all three stages of the injection molding process, from fill to pack to the warp. Now, just to give you an idea of what the pack and the warp settings look like, as far as the pack and warp settings go, I can change the pressure holding time and the amount of time I give the component to cool. I can also change the pressure profile applied during the pack stage, depending on my machine. Finally, as far as the warp stage go, all I need to specify is the direction of pull and the ambient temperature that this product is exposed to as soon as it's ejected from the mold. Now, taking a look at the results. Now, our two manufacturing criteria, I must say, were the fill time, which is about 0.9 seconds, which is a pretty good reduction from our last shot, which is about 1.1 second. Now, the pressure at the end of fill also reduced from about 64 megapascals to 61. And finally, let's take a look at what happened to the cooling time. Again, we've managed to reduce a whopping 10 seconds in the cooling phase of the analysis. Now, besides this, I'm also able to integrate what happens in the packing and the warping phase. For instance, in the pack phase, I'd like to see what the temperature distribution of the component at the end of the packing phase is, if it falls below ejection temperature. Now, finally, what most plastic manufacturers and designers are interested in is what the product looks like as soon as it's ejected from the mold. Now, I can look at the contribution to the warping of the product as soon as it's ejected from the mold, in terms of, hey, is it the packing pressure that's causing the warping, or is it due to the early ejection of the component not giving it sufficient cool down time? So, upping the deformation scale on the warping, I'm able to animate how the component warps and study the different directions of warp through this visual feedback. Great. Now, you will all agree the hardest part of being engineer is essentially compiling this entire analysis into one document. So what SOLIDWORKS Plastics has is also an automatic report generation tool. So here's a little Word document that I generated using the report generation tool. It essentially highlights all the material properties, all the data for the analysis, and the various results you get from the plastics injection molding manufacturing tool. Finally, there's one more piece of results output that I'd like to show you before I sort of conclude this presentation, which is the XY plot. Now, with the XY plot, I'm able to set a reference plane, and I'm able to study how a nodal point behaves as far as the temperature and pressure go, or how the temperature and pressure at that nodal point varies during the injection molding process. So right here, this indicates that point, the green point that you see on the screen, essentially takes about 8 seconds to fall below the glass transition temperature, giving you an idea of the part cooling time at that specific location. This is a great tool that you can use to identify anomalies such as gate freeze or freezing of your component that essentially causes short shots. Great. Now, jumping back into the presentation to summarize this little exercise. Now, as far as the optimized product goes, here are the results between the initial and the optimized design. So we managed to reduce fill time, the maximum injection pressure, and we managed to reduce the cooling time by about 10 seconds. Now, we've taken a look at how essentially we're able to manipulate our product with confidence in order to ensure its structural strength and manufacturability. Now, has this tool been used on field, and how close does this tool come to mimicking real life? So we work closely with UMass Lowell, SolidWorks does, in order to validate the results they see from actual injection molding with what they see from SolidWorks Plastics. So here's one such experiment. Now this is an electronics mounting plate. So we have a lot of areas or a lot of manufacturing defects that we hope that the plastics product would predict. And also one of the bigger areas is the warp of the tool, the little potato chipping of the tool that we try to mimic with the SolidWorks Plastics tool. Now the first thing we'd like to do is validate the fill state. So they run these shot experiments. Now what they do is they shoot about 20%, 60%, and 80% and 100% of the plastic volume on field and study how plastics actually tracks these shots. So you can see that the results between the plastics actually come pretty close to what we see on field. Now another big correlation was the sink mark profile. We managed to uh, compare or correlate the areas of the sink marks between the physical prototype and SolidWorks Plastics. And finally, the big result, warp. So this little potato chipping was also uh, mimicked in the plastic product. Finally, just to wrap up this little webinar, now what I'd like to justify are three things. Now, who is SolidWorks Plastics really for? Now, it's not only for the expert injection mold manufacturers who've had about 25, 30 years of experience. It's also for part designers who have just gotten into the entire plastics design process, who want to not only ensure the functionality of the component, but also make sure that it's manufacturable and work concurrently with their manufacturer, trading both part design and production information concurrently. Now, what SolidWorks does is it facilitates this little integrated platform for this concurrent development. And we also went through a short example that demonstrated that we were able to correlate real world results with what we saw from SolidWorks Plastics. Well, that's all for the webinar today. I know I went a little over time, but we definitely appreciate some feedback as to what you'd like to see in future webinars as far as the technical content being presented. And as always, this is Arun Thiraviam. Thank you for watching.